All right, howdy. This is a test of whether or not I can do lectures in my office on this minuscule whiteboard. So let's check it out. Okay, so what am I going to talk about? What I'm going to talk about is the inclined plane experiment. This was an experiment done early 1600s, I believe, definitely by a gentleman that you may have heard of, Galileo Galilei. Before he trained his telescope at the heavens and made a name for himself, particularly among the church, he did two very important experiments. One was the inclined plane, and the second was the simple pendulum. Through both of these, specifically the inclined plane, he was able to determine that that objects fall through a gravitational field, although he didn't call it that. He just simply said that objects fall towards the ground at the same rate, meaning they had the same acceleration. Now, the reason why he did it with the inclined plane, rather than say, as the story goes, dropping two balls off of the Leaning Tower of Pisa, is because with the inclined plane, you can essentially slow things down. So long as you take into account the friction involved between the block and the plane, then yeah, it's a great way of basically you are splitting or redirecting the downward vector, and that way you can slow the object's rate of fall, and you can see whether or not or you can measure what its, or calculate rather, what its acceleration is. So let me see if I can show it to you without embarrassing myself too much by forgetting stuff, and that way hopefully we can see have a real picture of what we're going on doing. So, yet again, my office is an example of why lefties get the shaft. I'm a lefty, which means I'm going to be doing this, which means you won't really be able to see me. And so, well, hold on, actually. Never mind. Look at that. All right. Anyway, so what we have here is, and I don't know if you can see that at all. Let me see if I can. Is blue a better color? I think blue might be a better color. All right, let's try this again. We have a plane on, we have an inclined plane. We have a plane or a chunk of wood or what have you, which is inclined to a flat tabletop surface. We then have a mass on that plane. Now, what you can do is, what we're really concerned with, or what we're most interested in, is when that block is in motion. So in order to get it in motion, you can do one of two things. You can either increase the angle of theta, basically make the incline steeper, and so you can watch it go, and then it will fall, because essentially your gravity becomes more of a downward, it has more of a downward effect on the block, because you can imagine if it were theta were 90 degrees, it's basically just free falling. Anyway, you can do that, or a nifty trick is, what you can do is you can just tap perpendicular to the inclined plane, let this thing bounce up down a couple times, and that basically breaks that static friction and actually will cause it to go down. Later, I may actually do something that describes the difference between kinetic and static friction. But for now, what I'm going to do is I'm just going to refer to friction as kinetic friction. So again, we are only interested in this block as it's moving and not sitting still like it appears on the board. So it will have a certain motion that way. Really hope you guys can see this. And I really hope it's not backwards. Oh, it will be backwards because Kepler is backwards. Video settings. Haha. Yeah, I really don't think you guys are going to be able to see this, but I'm going to try it anyway. Erasing sucks. Racing on this thing sucks. Anyway, so how do we do this? How do we show that gravity has anything to do with this? Well, I'll get to that in a second. For right now, all I'm going to essentially assume is that there is, in fact, something that causes an object to accelerate downward at some rate. So, and I'm going to call that a force. It's a caveat to this. I'm going to explain what I mean by that, what I really, really mean by that at the end of this. So for now, I'm going to call it a force. So what we do in physics is when we are encountering this sort of problem, is we draw what's called a free body diagram. We take the body like so. Oop. Yeah, good enough. Actually, no, I want to be consistent. Like so, and we draw all the forces acting on that body so we can have an idea of basically how are we going to apply Newton's second law of motion, because that's ultimately what we're trying to get to, is the acceleration of the body as it's moving in space. So what are the two forces? You can pause the video and put your answers in the comments, or you can just let me spoil it for you. Well, the two forces that are acting on this thing, three. So if you want to change your answers in the comments, do it now. There are three forces acting on this body. The first one, as I've already stated, is that downward force, which I am going to call FG. No. Let's not be cheeky. FD, downward force. Then, what else do we have? We have what is known as the normal force. The normal force is a upward force of an object as it sits on something. So this computer is not falling to the floor because the desk that it sits on, more specifically the giant book that it sits on, is in fact implying a downward or an upward force, which is combating that previously stated downward force. In that case, the total forces on my computer are zero, so it's not accelerating. So what about this one? What about in that case, the normal force is going up. What about in this case? Well, interestingly enough, the normal force is always perpendicular to the surface upon which it rests. Therefore, force normal. Oh, black is way cool, way better. All right, that's the mass. Down. All right. Then there's the third one, which I've already stated before, and that is friction. Now, friction always points in the opposite direction of motion. So we can intuitively, well, we can observe that the mass is going to slide down this ramp in that direction. So therefore, friction is in that direction. All right, now that we have this, let's talk about coordinate systems. And I'm not talking about Cartesian, spherical, whatever. I'm talking about basic plus or minus. What are we going to define as up? Later on, I'm possibly going to talk about, well, at some point, I'm going to talk about the idea of up and the idea of down, and why they are kind of nonsensical. But anyway, so what direction is positive? What direction is negative? I want you to, if you learn nothing else in this little talk, I want you to understand that positive and negative are what you make of it. I'm sure there's a psychological kind of tie in there somewhere, but you can define, you have this power. I believe in you. You have the power to define which directions are positive, which directions are negative. And so I am going to be using a Cartesian coordinate system. And so the way I'm going to define things may seem a little weird, or rather unexpected. What I've done is I have said that direction, or more specifically, the direction that is perpendicular to the inclined plane, is positive. And I have said that the direction up the inclined plane is also positive. Now, most folks, why it might seem unusual is that in everyday life, we kind of think of things in this way. Well, up is positive, and then to that direction or whatever direction, that's positive. Like I said, you can do that, but it complicates things, because ultimately what we have to do is we have to analyze or identify the forces that are only along one axis and the other. I hope you can see that with this coordinate system, we only have one of these forces that is directly along one of those axes. In fact, these two are at some angle relative to those axes. And so we would have to split two angles or two vectors into their components, which I will go into in a second. Whereas if I define it like this, then we have only one vector, which is, or one force, which is cattywampus to the axes, technical term. So we can see that the force normal as defined is the force which is perpendicular to the plane, the inclined plane, and then the force is along that plane. I define again that up, it perpendicular to that plane is positive, and along that plane going backwards is also positive. Where am I going? Why am I doing all of this? Well, the reason why I'm doing this is F equals ma, or more specifically, the summation of all forces acting on a mass times is equal to the mass of the system times the acceleration. And it's A, the acceleration, that I'm most interested in. What this summation means is really I am interested in what are the forces doing along the y-axis, or this up axis, up-down axis, this one that is perpendicular to the plane. And I'm interested in the x direction, which is along the plane. And so I've got two accelerations of note. I have the acceleration along the plane, and I have acceleration up, down, off the plane, into the plane. Well, hopefully you can see immediately, we can simplify this a bit. Because the motion, because as you would, if you do this, your own self, you will find that the block will not rise off the plane, and it will obviously not sink into the plane. So therefore, that is equal to 0. And so therefore, all of the forces in the y direction must equal zero, must come up. Basically, there must, if you have one force that is going down, you must have an equal and opposite force which is going up. Because again, block is not moving into the plane or out of the plane. But with AX, it's not the case. That is the key. So, because my board is minuscule and I am, screw. Theoretically taller than the average bear, I will pop a squat. So, as I said, F, Fn, and little f are along the axis, so I don't have to worry about this. I have to do something about this, though. And so, what I need to do is I need to determine, I have to what we call split that vector into its components. I have to figure out what part of that vector is acting along that, what part of that downward force is acting in my negative y direction and in my negative x direction. And the way to do that is, as it happens, and I'm not going to show this in this video. I leave that to you as an exercise for yourself. As it happens, that angle here is the exact same as that angle there. Again, you can use geometry to prove that to yourself or to show that to yourself. Now I'm going to use geometry, or now I'm going to use trigonometry, SOHCAHTOA. So what sine, the function sine, is the length of the opposite leg to the hypotenuse of that triangle. So if I'm interested in this, my x vector, then what that is sine of theta over d, or FD sine theta. But remember, always pay attention to your negatives. That is negative. I defined up that way as positive. This is going that way as a negative. So what about the other side? Well, the other side is that's the SOHCAHTOA. Then you got the COA, which is the cosine. I don't know. I'm losing that analogy. The cosine is the adjacent over the hypotenuse. Yeah. Ka. So, can you guess what I'm going to do next? That's right. If you said put a negative sign in there, you would be correct. Ta-da! Because again, this is my coordinate system. This way is negative. Up is positive. Sorry for that. So now that I've got this split up, I can now draw or write out the summation of all the forces in any particular direction. So yeah, I am going to lose my eraser. Okay. So sadly, I'm going to have to erase this. So please keep this in mind. If I have to come back to this, I will redraw it. But please, hopefully you have all of this in mind. My wall sadly only has, so much space. Exoplanets need to be hung. So there you go. Anyway. So going to this, what are the forces in my y direction? Well, we have the normal force. Again, I'm just about to figure the drawing, and I've just erased. Anyway, hopefully remember normal force going that way. I really need to not use that arm. So we have normal force. It's along that axis and it's positive. Then we have this, which you can't see because of my big fat belly. So here, if you can't read it, sum of the forces in the y direction equals the normal force minus the downward force times cosine of theta, the angle of inclination. Now let's write out the x direction. So here we have, in the x direction, again, because of that, friction is positive, and we now have minus downward force times sine of theta. Easy peasy. We know that this, again, from over here, is 0. So Fn equals, so Fn equals downward force. Sorry, gotta pop up. I don't care about Radical's new video. The normal force is equal to the downward. The normal force is equal to the downward force times cosine of theta. That will become important. What about x? Well, x and this is equal to ax. Yes, ax. So again, what we're looking for is ax. So we have friction minus downward force over mass of the block. So now, how do we quantify? How do we quantify what F is? The frictional force. And as I said with Galileo, he had to know this. He had to come up with some independent way to figure out how much friction there was between, say, a oak block and a maple board. How much resistance does that block have when it's sliding down that board? Well, if you do the experiment, if you do that type of experiment with enough data points and enough a large sample size, what you find is that the frictional force is equal to a constant times the normal force. This is known as the coefficient of friction. To be specific, since before I was talking about the fact that I'm just labeling friction, what I'm really talking about is kinetic friction. And so this would be F of K, mu of K. So this is technically the coefficient of kinetic friction. Now, if you're wondering why, if you have a block on an incline and it doesn't move, if you do the tappy tap and it starts to slide and it continues to move, why is that? Why doesn't it just stop again? Why doesn't it move and then stop? because what we're dealing with is two types of friction. The first one is static friction. It is the friction which opposes any kind of initial motion. And then you have kinetic friction, which is the kind of friction that opposes any kind of ongoing motion. They're both the same equation. So that's kinetic. That's static. The difference is that coefficient of friction. The coefficient of static friction is going to be higher. It's always going to be higher than the coefficient of kinetic friction. So hence why the static frictional force is larger than the kinetic frictional force given the same block on the same plane. And if you have a larger force, as you can see here, that larger force may be equal to or greater than this downward force, this component of the downward force, so the acceleration can be zero or negative, which is non-physical, basically zero. Actually, negative would be indicated that it's going to go up the ramp, but trust me, friction can never do that. Friction never goes, is never going to be, doesn't power anything to go up or go in its direction. All right, so hopefully that wasn't confusing. So yes, so kinetic friction is always going to be lower than, kinetic friction is always going to be a smaller force than static friction because the coefficient of kinetic friction is always smaller than the kinetic friction of static friction given the same materials. At the outset, I said we're only dealing with the situation where the block is moving, and so it's kinetic. And since I don't really want to draw a whole bunch or write a whole bunch of subscripts, I'm just going to leave it out. So just imagine f of k and mu of k. All right, so you got this. Remember how that I said that was important? Because of this. All right, now I have to do more erasing. I'm going to erase this stuff. How did I lose the eraser again? No, serious. Ah, there it is. My coat was hiding. So now we have we can rewrite this. We can rewrite this. You have AX, again, just in case you can't read it, AX equals mu, the coefficient of friction, times Fn, the normal force, minus the downward force times sine theta, all of that divided by the mass of the block. From here, we can substitute in for Fn. Now it's, again, the acceleration in the x direction is equal to the coefficient of static friction times the downward force, cosine of theta, minus FD, the downward force, sine of theta, over m. Okay. I'm trying to think of where I'm going with all this. So without, again, trying to embarrass myself. So you have that acceleration. All right. Now, what are we going to do with it? And obviously, we don't know what the downward force is. You can look up in a book or these days on the interwebs, as far as I've heard. You can look up what that coefficient is. Again, if you know specifically what the materials are. You know angle, or you know theta, because you can literally measure that angle with a protractor. Mass, you can measure because any kind of digital scale or 3-balance thingamajiggy, technical term, you can measure the mass. So, what is this downward force? Or actually, let me back off that for a second. What about this acceleration? Where can we get this acceleration? Well, glad you asked. What we can do is we can use a part of physics known as kinematics. Yes, I have the most awesome singing voice. I often get told that. Specifically in kinematics, there is an equation that relates the distance something travels to the initial velocity. Where do I want to go with this? Involves time and this is probably where I'm going to embarrass myself. Let's see. Hold on a second. Let me do some magic. Aha, I remembered. Oh, the dementia hasn't got me yet. So the equation is x, or really the change in x, how far it moves, is equal to the initial velocity of the body of the mass in the x direction times t minus plus 1/2 ax t squared. All right. So now we have two measurable quantities. We can measure how long or how far it travels, and we can measure the amount of time it takes to get there. But what about V0? Well, poop. I don't know how do I get the initial velocity of the block? Well, you can use kinematics. I am a dummy because I was thinking to myself, well, if it's moving, then it has initial velocity. But what I failed to take into account is that what we're looking at is basically right as it starts to move. Therefore, the initial velocity is zero. It starts at rest. Hopefully there wasn't too many people out there in YouTube land who was screaming at the screen, "Hey, yo, Rob, it's Professor Parks, it's zero, zero." I know I'm doing that now. Anyway, so that goes to zero. So what we have is that. Again, if you can't see it, AX is equal to 2x over t squared. So very simple. If you have a stopwatch and you have a ruler and you have a protractor, you can measure everything you need in order to get essentially that quantity. You can measure, well, really, you don't even need the protractor. You know the distance, you know the time squared. You can tell, you now know what the acceleration in that x direction actually is. So, where's gravity in all this? Well, this is how the science works. Is I've come up with an empirical test. I have a block on an inclined plane at a particular angle, which I have measured. That plane, the course of the block's motion, I can also measure. I allow that block to go from rest down to the end of the block, or end of the plane, and I can measure that time. So I know to a certain precision what this AX is. So we know through that previous analysis that AX is equal to this, mu FD cosine theta minus FD sine theta all of that divided by m. This is where science comes in, is now you can test various hypotheses. I'm going to test whether or not Newton's law of gravity works. I'm going to test whether or not if I assume Newton's law of gravity, whether or not I can calculate what this AX is, and then I can compare it to this AX, which I measured. Now, if they're the same, or rather the same within the error bars that are in this, again, you can only measure this to a certain precision based on your instruments. If this is equal to that within the error bars, then you have shown that your hypothesis is true. Now, I'm not going to go into various other hypotheses, but if you think that gravity, for example, ain't a thing, and you can plug in you can do this exact same methodology. This is the scientific method, but you can do the exact same methodology with any other hypothesis. If you want to say that FD is equal to density disequilibrium, for example, that density is the thing involved, then you need to come up with a formula for density, and then you need to basically do what I'm about to do. If you think it's electrostatics, that that the block is somehow positively charged and the ground is negatively charged and it falls down, then again, you can use Coulomb's law to do what I'm about to do. So let's get into it. I'm going to erase this side and I don't know if you can see that any better, but like I said, I will speak and oh wow, I am not using that because that doesn't erase. Green? Great. All right. Could have done the slide, but all right. So, what is Newton's formulation for gravity? Newton formulated that the force of gravity is equal to a constant, now known as the gravitational constant, times one mass times another mass divided by the separation of those two masses squared. All right. Now, it has been well studied, and if you want a fantastic practical example of this quantity G, this gravitational quantity G, has been measured many, many times to various different precisions, and they all agree within their error bars. Blue came up with his own measure, and lo and behold, his experiment, which is now at the University of Tennessee's, where it's being used to teach undergraduates, that's his G agreed with everybody else's. Hey, look at that. Science, repeatable. Awesome. Now, in this case, what is M1 and M2? In this case, I'm going to say that M2 is the mass of the block. That I'm just going to refer to as M. M1 is the mass of the Earth. Now, what is R? R, very specifically, is the radius of the Earth at your location plus the height of the block at the top of the incline. Now, I say that because, again, I'm trying to be very specific. The reason why I didn't say the radius of the Earth is because the Earth is not a perfect sphere. The Earth is oblate in that its equator is slightly more than the poles. And force of gravity, again, is between the centers of those two masses. This block is not sitting on the ground, so therefore there's an additional height. But my assumption is that given the level precision of your typical instruments, a protractor, a triple beam balance, and a ruler, that the difference in the radius at your location to the average radius of the Earth, assuming that it is a sphere, is minute. And also, and even more so, that the distance off the floor is minute. That you're not going to see a difference in the sense that you're going to get some kind of factor. Spoiler alert, it's 9.8. If you actually count for everything else, you're going to get some number in the back end. If you don't account for it, you're going to get a slightly different number, but it's going to be on the back end. But your instruments may not be sensitive enough to see this, to see the back end. All they can see is that 9.8. That is the confidence on which you can hang your measurements. If you get more precise instruments like a micrometer, like a atomic clock, or some kind of even more sensitive, ridiculously sensitive protractor or drawing compass or what have you, then you can have the precision. You can add more decimals. You can believe more decimals in when you compute acceleration from 2x over x squared. But for this so that is something also you have to keep in mind when you are doing science, is that you have to understand at what level can you trust the measurements of your measuring tool. For for a ruler, say, which I have one around here somewhere. For a ruler, say, which you probably cannot see, this is to 1/16. I can measure like the bars are to 1/16. Canonically speaking, what we accept is that the error bar is 1/32 or 1/2 1/16. So you cannot believe any number that you measure to a finer precision than 1/16 or than half, well, than to 1/32. That number you can be certain of. If you try to measure to 1/64th, no, there's no way you can measure that and have confidence that that number is correct with this. You need something better. Okay. So now, given that, I am going to make the assumption that the mass of the Earth, we're just dealing with the mass of the Earth, and we're just dealing with the radius of the Earth. I am not going to look up those values. I'm not going to tell you what those values are because honestly, I don't keep those in memory. That's why I have books or this interwebby thing that I've heard of. But I'll leave it to you to find out what these values are and test and see if I'm lying to you. You can also find out what G is. G is like 6.6 times 10 to the negative 11 Newton, blah, 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 blah. Unit. I know, I'm being very professional. But you can look up these values from a trusted source. What I'm going to tell you is that I am actually getting ahead of myself. Let me rephrase. So this is the downward force. This is my hypothesis. This is the downward force this is the force that I believe is that downward force. Well, if we go to Newton's second law says a force is equal to the mass times an acceleration. So if this is a force, if this force is this, then this acceleration is the acceleration due to gravity or as a result of gravity acting on that mass. So I'm going to call this G. Now this is where I was going with it. If you make the substitution, lo and behold, Galileo was right. Mass of the block don't matter. Doesn't matter if it's a giant boulder of a block or a giant huge oak table or a itty tiny oak doorstop. Doesn't matter. Doesn't matter what the mass is. So now you can look up those values that I was talking about, and you can calculate that G is equal to 9.8 meters per second squared. Near sea level, it's actually 9.81. At mountain height, it's like 9.80. So that kind of gives you an idea of the range that this acceleration can change. And again, at mountain level, you're adding the height of the mountain to the height of, or basically the radius of the Earth. So you have G is 9.8 meters per second squared. So if we go over here, what we can do is we can replace this downward force with mg, or gravitational force is equal to mg. I'm assuming downward force is the gravitational force. So voila. That I'm positive you can't see, so but I will read it off to you. AX is equal to the coefficient of friction times mass times the gravity, that quantity minus, oh, I'm sorry, times the times cosine theta. Let me back up. The acceleration is equal to the coefficient of static friction, kinetic friction, times mass, times gravity, times cosine of theta, minus the mass of the block, times gravity, times sine theta, all of that divided by the mass of the block. Lo and behold, again, mass of the block don't mean anything. Goes away. Doesn't matter if it's a oak desk, oak oak doorstop. I really like oak, if you haven't figured that out yet. So, la 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 la. You can do the mathy math here, or maths if you're over on that side of the pond. Oops, that's not what I wanted to do. Actually, yeah. So now we have that G, the gravitational acceleration, which we expect from Newton's law or Newton's law of gravity. That is equal to coefficient of static or coefficient of kinetic friction times cosine of theta minus sine of theta divided by AX. From our kinematics, we know AX is 2x over t squared. Plug that into here. Plug that into here. We have a G equals t squared. So the gravitational acceleration is equal to the coefficient of friction, cosine theta minus sine theta, that quantity, times the time it takes to go down the ramp squared, divided by 2 times the distance that the block travels. You can look up the coefficient of friction. You can measure all of those variables in that in Galileo's experiment. You can then calculate the value G, or the acceleration due to that downward force, because of this. If that G matches this, that G is 9.8, something. then you have validated that gravity is the reason for that downward force. All right, I believe that I am done. Oh, one last note. Like I said, if you challenge the idea that gravity ain't a thing, I just remembered something. If you challenge the idea that gravity ain't a thing, then what you can say is, I think force is the electrostatic force. Then you can say that, what is it, Q? Coefficient of, I think it's Q. Honestly, I've forgotten. The dementia is slowly creeping in. The coefficient of the electrostatic coefficient times the charge of the block times the charge of the Earth divided by the radius of the Earth squared. That's equal to MAX. And you can then follow that down. At that point, you're going to start needing to measure charges, which there are ways you can do it. And then you can see it that way. This is how science is done. Last thing I'll leave on is that whole force thing. You might think, Professor Parks, you've been on record many times saying that gravity ain't a force. And it isn't. But what I can say is that gravity is a consequence of curvature of space-time. And that can be described by Einstein's field tensor. If you solve that field tensor in the limit of velocity going to zero, or probably better said, really slowly, then that acceleration simplifies down to Newton's law. And again, if you don't believe me, you can look that up. Maybe at some point I might actually derive that for you. But for now, I'm just going to state that Einstein's field tensor, when taken in the limit of very, very small velocities, canonically, it's usually 10% the speed of light or less, then that equation to describe the acceleration due to the curvature simplifies down to Gm Earth m block over the radius squared, or rather the distance squared. All right. Well, I am going to leave this unedited and see what happens. All right. Peace out. Clear skies.